So this clip is my attempt to convince you that using the Wolfram Online Platform is a gem, especially when it comes to exam revision and preparation. So I assume you have signed up, and if you haven't, on Blackboard, if you look at my first online clip, you can learn how to do it. So let's just go to the Wolfram Online Platform, and we go to the development platform. Okay, and I have a number of files which I've already used. They're all in my home directory, and I go to this one, Univariate. Okay, so sometimes when you return to a file, if you've done some work and you previously did something, it's possibly good to go to reset session. So you can also write stuff. That's what I've done here. I will publish this file as a PDF file on Blackboard, so you can work with it. So let's do some univariate work and see how you could use Wolfram to check your work. This is a question taken from a tutorial. So we have a function x minus x to the negative 1, so that's x minus 1 over x. We are assuming that x is unequal to 0 because we are dividing by x and we couldn't divide by 0. And the question was, which of these following statements are true? The function is concave, the function does not have a stationarity point, and the second derivative at 1 is larger than 0. So we have to do some work. So firstly, we need the first and second derivatives for sure. We want to have a stationarity point. We need to set the first derivative equal to 0. So let's see how we do these sorts of things. Of course, you will be expected to be able to calculate these derivatives by hand. This is to check your work, not to do your work, because in the exam you don't have it. How do you check that your first derivative is right? So this is what you do. You go, if you were to write it again, you see there's a little horizontal cursor which appears and a plus, and you say Wolfram language input, and here you would type. Now I've done this typing already such that this clip doesn't get too long. So what you type is a big capital D and then in square parentheses the function, which is here, x minus x to the negative 1, and then we want the first derivative with respect to 1, and we want the first derivative, sorry, with respect to x, that's the variable for the derivative, and we want the first derivative. And then have your cursor in here and press Shift Enter, or go to evaluation and say evaluate cells. And here is your first derivative. So you check that against your work and make sure you're right. This is correct, of course. I've saved this F1 equals that just means that from now on, when I say F1, Wolfram will know what I have in mind is this function. So let's get the second derivative. It's basically the same, just that here I'm saying I want the second derivative. Okay, so again, cursor in there, Shift Enter. Here's my second derivative, negative 2 over x to the 3. Okay, so again, you would have calculated that by hand, but now you can check whether you're right. So at this point, we can go to the second statement and we can try and evaluate that. The function does not have a stationarity point. Now, a stationarity point, we know what we want to do is we want to set this first derivative equal to 0 and find which value of x solves this. So how do we do this? Say solve, and here's our first derivative. You could have tried with just putting f1 in here, but that's the result of our first derivative, 1 over 1 plus 1 over x squared. So 1 plus 1 over x squared. And we are setting that equal to 0. Now, we're really doing some programming here, and we're using this double equal sign to set something to 0. Okay, that's just a little quirk of programming language you have to see. So we are using solve. So this command will solve something. It will solve this equation, the first derivative set equal to 0, with respect to x. Now let's actually try first without this last term and see what happens. So Shift Enter, and we get some funny sort of stuff, okay, which I don't want you to understand. The issue is here is that if we are using negative x's, what happens then? Sometimes we already know that our x is unequal to 0. Okay, and one way how you can tell this, and that's just a little quirk you may need to know, is you say reals for real numbers here. We put a 0 in, or we put that in, shift enter, or evaluate this cell, and what we get is this empty term, and that means there is no solution. Okay, so this implies that there's no solution. Okay, clearly if you had looked at this, you could have found that, because there's no way that you can set this term equal to 0. So that means B is indeed correct. So then to establish A is this function is concave, we need to establish what happens to the second derivative. For the function to be concave, the second derivative always has to be negative. Okay. However, if you look at the second derivative, which is here, you can realize that this x to the 3 can be negative or positive. Okay, so the overall term can be positive or negative, depending on what x3 is. So we can already, looking at this, we realize, okay, we cannot say that the function is concave across the entire domain or not. Now, let's say that wasn't so obvious. Why don't we just look at what the function f2, the second derivative, looks like? The way how you do that is with this plot command. Okay, plot in square bracket our function f2, because we assigned that up here to this new term f2, and we want to plot it for x in the range of -5 to 5. We could actually choose, that's just for the fun of it, choose some other range, and then shift enter again, and here is our second derivative function. Okay, that's basically this function plotted. Okay, and you can see it can take positive values. So here we're in positive range, here we are in negative range. It can take positive or negative values. So that means we cannot say that our function is concave. So that means A is false. Now, lastly, we want to know whether the second derivative at value 1, whether that is larger than 0. Now, we can already see from that graph, at value 1, our second derivative is actually negative. Okay, so we could already answer and say that this is not true, but we could also just let Wolfram calculate what the value of the second derivative at x equals 1 is. We do that like this. f2, that has saved our second derivative, and then in round brackets we say at what value of x we want this evaluated. We say shift enter, and we find the value is -2. Okay, of course we could have read that from the plot at x equals 1, the value is -2. Okay, so the functions we have used here is finding derivatives. We solved an equation, we plotted a function, and we calculated the value of a function. All of this you can do in Wolfram. That means you can use Wolfram to test. If you had to do any of this, you can use Wolfram to test your work.